All right, let's dive into a classic problem from multivariable calculus. How in the world do you find the exact area of a curved 3D surface? Think about the top of a dome or the side of a mountain. It's a fantastic puzzle, and the solution, it turns out, is incredibly elegant.
So to really get our heads around this 3D problem, let's rewind a bit. Let's go back to a 2D idea you've probably seen before. How do we measure the length of a curve? You know, not a straight line, but something with all kinds of twists and turns.
Well, a trick you might remember is that we chop up that curve into a bunch of teeny, tiny, infinitesimally small straight lines. We know how to measure the length of a line, so we just add them all up using an integral. That's the whole idea behind arc length. Now hold on to that thought, because it's going to be important.
Okay, let's bring that idea back to our 3D challenge. If we use tiny straight lines to approximate a curve, what do you think we might use to approximate a curved surface?
Exactly. It's the same idea, just bumped up a dimension. We imagine these tiny little flat patches on the XY plane, the floor, and we project them straight up onto our curved surface. What we get is a tiny, tilted parallelogram, basically a little tangent plane. So to get the total area, all we have to do is add up the areas of all these little tilted planes.
So this brings us to the tool that does all the heavy lifting. We need some way to figure out exactly how much bigger each tilted patch is compared to its flat shadow down on the floor.
And here it is. I know. At first glance, this double integral might look a little crazy. But honestly, the part under the square root is the real hero here. That's the engine that figures out the steepness of the surface at every single point.
We're going to give this thing a name, the tilt factor. See, it takes the partial derivatives with respect to x and y, which are just the slopes in those directions, and it combines them into one single number that tells us exactly how tilted our little plane is. For those of you who want to nerd out for a second, this whole thing actually comes from the magnitude of the cross product of two tangent vectors. It's a beautiful bit of linear algebra that perfectly measures the area of that little parallelogram.
All right, enough theory. Let's get our hands dirty and see this formula in action. We're going to start with a shape you'll see in pretty much every calculus course, a paraboloid.
So I want you to picture this. We've got a bowl, and its shape is described by z equals x squared plus y squared. We're going to slice the top right off at a height of 9, and our job is to find the surface area of the bowl part that's left.
And here's our game plan. It's a clear, step-by-step process. First, we'll find those partial derivatives and build our tilt factor. Then, we'll figure out the shadow region on the xy plane and pick the best coordinates for the job. And finally, we'll set up the integral and solve it. Simple as that.
All right, let's start crunching the numbers. The partial derivative of our function with respect to x is just 2x. Easy enough. With respect to y, it's 2y. We plug those right into our tilt factor formula, square them, and simplify. And hey, look what we've got inside that square root. That x squared plus y squared term? That is a huge clue for what's coming next. Yeah, anytime you see an x squared plus y squared pop up in a double integral, that should be like a giant flashing neon sign in your brain telling you to use polar coordinates. It just makes life so much easier. Not only does our tilt factor simplify to the square root of 1 plus 4r squared, but look at our region. The shadow of the bowl on the floor is a perfect circle with a radius of 3. Polar was made for this.
Now I gotta stop here for a second and give you a super important warning. When you make the switch to polar coordinates, that little area element, dA, becomes r dr d theta. Forgetting that extra r is, without a doubt, the single most common mistake students make. Seriously, don't let it happen to you. It's absolutely crucial for getting the right answer.
So here's our final setup. Theta runs from 0 to 2 pi to go all the way around the circle, and our radius, r, goes from the center out to 3. And look, that extra r we just talked about makes this integral absolutely perfect for a quick u substitution. You run the numbers, and there it is, our final area.
Okay, that was a bit of a workout, right? A lot of moving parts. So you might be wondering, does it always have to be this intense? Let's put our formula to a different kind of test. Let's dial it back and try something way simpler. A flat, tilted plane. If our big, fancy formula is legit, it better give us an answer that we can check with basic geometry. It's a good sanity check. Let's see if it holds up.
So here's the problem. We need the area of a triangular slice of a plane that's bounded by the x, y, and z axes. Just think of it like a tilted sheet of glass stuck in the corner of a room.
And guess what? We use the exact same plan. First, we get z by itself, then we find our partial derivatives. The derivative with respect to x is -2, and with respect to y, it's -3. And we plug these constants right into our tilt factor formula.
And look at that! Our tilt factor is just a number, the square root of 14, which makes total sense, right? A plane is flat. Its tilt doesn't change from point to point, so its tilt factor should be a constant. This is exactly what we'd expect.
And this is where it gets really cool. Since that tilt factor is just a constant, we can yank it right out of the integral. The whole problem just simplifies to the tilt factor times the area of the shadow region D. Well, that shadow is just a triangle on the floor with a base of 3 and a height of 2, so its area is 3. The final answer? Simply 3 times the square root of 14. Beautiful.
All right, for our grand finale, we're going to do something really satisfying. We're going to use all this calculus machinery to prove a formula you probably learned way back in geometry, the surface area of a sphere.
So we start with a classic equation for a sphere with some radius a. As a little shortcut, we'll find the area of the top half and then just double it. Now, you got to solve for z, find the partials, plug them into the tilt factor, and after a whole bunch of really careful algebra, trust me on this one, the expression simplifies down beautifully into this, which just depends on the radius a.
Then you set up the polar integral solvent, and you find that the area of that top hemisphere is 2 pi a squared. And when you double that to get the whole sphere, boom, 4 pi a squared, the exact formula you learned in geometry class. We just proved it from the ground up. How cool is that?
So after all that, let's boil it all down to a simple 3-step master plan that you can use on any of these problems. This is your go-to strategy.
It really just comes down to this. Step 1, find your partial derivatives and build that tilt factor. That's your integrand. Step 2, figure out the shadow of your surface on the xy plane. That region D gives you your limits of integration. And step 3, put it all together, build your double integral, and solve it. Use polar coordinates if you see that x squared plus y squared. So we've totally nailed how to handle surfaces where z is a function of x and y. But what about the weird stuff? What about a donut, a torus, or a cylinder standing straight up? Our tool, as is, kind of breaks down for those because you can't solve for z as a single function. So how would we have to change our approach to measure those areas? Well, that leads us right into the really cool world of parametric surfaces. Thanks for watching.